Okay, good. Then let's get started, everybody, for our computer vision, robot vision course. This is the second, little bit more advanced course on computer vision that I teach here at NTNU. If you took the course last year, last semester, then topics will be slightly different, a little bit of overhead in the overlap in the beginning. Now, first of all, I need all of you to sign up for Discord because the course also has quite a large virtual component. And so go and create a Discord account if you don't have it yet, and then join this particular server. And do that now so I can give you the correct permissions to access the robot vision lecture material.
Yeah, yeah.
So at the moment, this is the main conduit where I post all the lecture materials, announcements, and things like that. That will all happen in the Robot Vision channel. Eventually, we may switch to Matrix later on in the course. I'm just testing that at the moment. The reason is that I used to have a nice setup with my bots, to help me with administration. And then Discord changed their policies, so I couldn't run the bots on the free channel anymore. So I think a open source solution that I can run on my own server will be preferential, so that doesn't happen again in the future. So I'm switching a lot of the things over to Matrix at the moment, but I will let you know about that. Now, the course is a couple of things that you need to be aware of for the course. First of all, the assessment. Actually, first of all, consists of 4 parts. There's a 20% assignment 1. There's a 20% midterm. There's a 20% project and a 40% final exam. And the topics of the course, like it says in the calendar, are computer vision topics relevant to mobile and other types of robots. Now, I'm a little bit surprised today because the last week we had fewer students, so quite a few students showed up new today.
No.
So that's okay. I'll give you a chance to introduce yourself in a little bit. So at that point, maybe you can explain why you decided to take the course at this point in time. So what we're going to do today then is we're going to start with a short introduction about myself and my research. And I'll just show a couple of videos of the research that we've done and some of the motivation behind it. And then I'm going to ask you to introduce yourself. So from you then, I want to know your name and your university background. So that would be, I'm now first year master student at NTNU, and I got my undergraduate degree from TKU or something like that. Or I'm a third year bachelor student from, I don't know where, Australia University. Then I would like to know your robotics and programming background. So tell me a little bit about the projects that you've done, as well as the programming languages that you know, C++, Python, Java, TypeScript, what have you. Okay, just what programming you've done. Then would like to know about your hobbies. So what you like to do when you're not studying. And lastly, about your, the last question I just came up with today. So the last book that you read.
Let me just.
Okay, so I'll start with a little introduction about myself. So, my name is Jacob Baltes, and I'm a professor here at the National Taiwan Normal University since 2016. I actually did my PhD at the University of Calgary in Canada. I'm born in Germany, but I did my PhD at the University of Calgary in Canada, where my topic was actually one of the traditional AI topics of its time. It was a planning problem solver for a kitchen robot. But that was 1996 when I graduated. So at that point, we didn't actually have power. We still don't have powerful actuators, not as powerful as we would like them, but at that point, the actuators and the sensors that we had were extremely poor and extremely expensive. So, like most people, my planning system was only running in simulations. But then in the simulation, you had a little kitchen robot that could cook for you or make drinks for you. And the problem, this particular task is difficult because in order for the robot to make a cup of tea, it would have to reason about the actions that it could do. And so then it would reason that to make tea, I need to drive to location 22, I need to pick up the cup, I need to drive to the table, put the cup down, open the drawer, pick out the tea, put the tea down. I made a mistake, now I already have the cup. Usually I pick up the cup out of the drawer, out of the cupboard. So pick up the cup out of the cupboard, put the cup down, close the cupboard, pick the cup up, drive over to the sink, put the cup down, turn the sink on, put the cup into the sink, wait until the cup is full, turn the faucet off, pick up the cup, drive to the microwave, put the cup down, open the microwave, put the cup into the microwave, close the door of the microwave, turn the microwave on for 1 minute, wait, open the door of the microwave, pick up the cup, put the cup down, close the door of the microwave, pick the cup up, drive back to the cupboard, put the cup down, open the cupboard, pull out the tea box, put the tea box down, pick up, take the lid of the tea box, put the lid down, pick up the tea bag, put the tea bag in the water. Now wait 3 minutes, you have tea. And the issue when trying to generate a plan like that, initially it seems very trivial because you can just design an algorithm where you say, I have the current state, whatever the current state of the world is, and my agent has a number of possible actions. In my case, the very simple kitchen robot had the actions of being able to drive to different locations. Right? So it had a bunch of actions that could move it around. And then it had a gripper that it could pick something up and put something down. So this is a very, very simple robot. But even there you have, with the different locations that you could drive to, you had about a dozen different actions you can execute. Now, the robot is time t0, we're here, then we drive to a different location, now we're in time t1. Now I can again apply different actions, like picking something up. And if I keep doing that, then eventually I'm going to find a state of the world where I have a cup of hot tea, and then my plan will be solved. So the reason why that doesn't work is because of the computational complexity. The fact is that if I have, and you can see like a real robot would have a lot more actions, right? Every motor that we can move. So there will be hundreds of possible actions or an infinite number of actions that we can execute. But even a simple robot would have 10 actions. So then at the first state, there's 10 possibilities, but then each one of these 10 has another 10 successor states, right? And each one of those, I have 10 possibilities. And that means the number of nodes that I have, not even in the tree, but just at level k, right? The number of nodes at level k would be so at level 0 I have 10. Actually, usually we start at level 1, I have 10 nodes, right? At level 2 I have these 10 nodes. Each one of those has 10 successors, so in total I have 10 times 10 is equal to 100, right? So at level k, I will have 10 times 10 times 10 k times, which is 10 to the power of k. Right? Now, if there's some goal state here, the t state, then that algorithm will actually get me there. And not only will it find a solution, it will also find the shortest solution in the sense of the least number of actions that I need to execute in order to achieve my goal. The problem is this complexity of 10 to the k here, because as you've seen, in order to make t, that's already about 10 steps. Okay? So even for that, my robot will have to do the amount of work that it needs to do is 10 to the 10, or about 10 billion. Now, if you want to make Neo-Roman, that would be a lot more steps. So you'd be looking, maybe it takes you 100 steps to make proper dinner. And the problem is, if you plot this, then the complexity curve will look like that. The runtime of your algorithm is going to explode. And it's going to explode not just, oh, takes a long time to calculate, maybe my computer will run for an hour, or a day, or a week, but it will run billions and billions and billions of years. So there's no possible way to do it, to approach it in that way. Anytime you're implementing an algorithm that has this kind of complexity, you need to be very careful to make sure this only works if your k here is very small. If you know you can do it in 3 or 4 steps, then that's not a problem. That's 10,000 nodes. You can calculate that in 1,000 nodes per second, so then about 10 seconds. Right? But if your k is anything that we would be required for the kind of plans that we want our robot to execute in the real world, then this kind of complexity, 10 to the 100, is completely intractable. One number that I like to keep in mind always is 10 to the 80, because that's a number of estimated primitive particles in the entire universe. So you think about the Earth, all the atoms in the Earth, right? And then the solar system, and Jupiter is so much bigger than the Earth, and the Sun is so much bigger than the Earth, and then that's a tiny part of the Milky Way, our galaxy. Then you think about there's billions and billions of stars in the Milky Way. Then you have billions of galaxies, Andromeda and 84, and so on and so forth. All of this matter together, right, consists of atoms that have a different number of protons and electrons. And if you have an algorithm that has a runtime cost, estimated cost of 10 to the 80, you're talking about an algorithm that goes and enumerates each one of the protons and electrons in the universe. So there's no hope to do that on a computer. And even if you say, oh, next year I'm going to have a faster computer, maybe you can do it 1,000 times faster, it's still not going to be able to give you an answer within the lifetime of the universe, never mind your own lifetime or the deadline of when your assignment is due. So that's the kind of problem that I was working on, to bring that complexity down. And of course, humans have the same problem. We obviously can't run this particular algorithm either. So humans have developed many different problem-solving strategies. Things like abstractions. If you listen carefully to the example with the T, you realize that the current position of the robot is not really important, right? Because it's only important if I want to use the microwave. But if I want to use the microwave and I'm at a different location, I can always just drive there. And the other parts of the important parts of my state space really don't care about the location. They only care about what I'm holding in my gripper. Before I drive to the microwave, I have to have a cup with water. Otherwise, it doesn't make sense to drive to the microwave. So you could break that problem down into two layers, where at the top level, your planner only cares about what the robot can pick up and put down. And then when you have a plan for that, then you can figure out the movement, the driving commands you need to send to bring the robot to the correct location. So abstraction is a very powerful problem-solving strategy. It means that we ignore low-level details of the problem until they become relevant. Other problem-solving strategies and the system that I wrote, it was kind of pretty clever in the sense that it would modify the actions that it has available. So another thing that you may have realized is there's quite often that we're holding an object, then we put it down, then we open the microwave, then we put the object, pick the object back up. And for that, then the system would actually learn that this sequence repeats very often, and it would combine that into a combined operator. So then instead of having 10 operators, it would have 11 operators, where the 11th operator would be a combination of previously primitive operators that consisted of putting something down, doing an action, and then picking something back up afterwards. Another problem-solving strategy is case-based reasoning. Case-based reasoning means that if my robot knows how to make tea, then like just straight tea, then before it would try to make tea with sugar, or if it knew how to make tea with sugar, and then you asked it for coffee with sugar, it would actually redo only parts of the plan that have to do with the difference between tea and coffee, but the sugar part would remain the same, because that can be dealt with smoother. So case-based reasoning is the idea that we have a solution for some other related problem, and then instead of planning from scratch, we start using that previous solution, and then we try and fix it, repair it for the new situation. And there's many other kinds of problem-solving strategies that people have developed. So then, when in 1996 I got my PhD and then started my first job as a professor at the University of Auckland in New Zealand, then I started thinking, I'm going, actually, this was all done in simulation. And to just be able to implement a computer program that can pick up a cup, that action in itself in my system was one primitive action. So it was very simple. I just applied it and boom, I was holding the cup. There was no problem with trying to figure out where the position of the cup is relative to the robot. As long as it was in the same location, the robot would be able to pick it up. There was no problem with trying to detect the cup in the world in the first place. But all of those problems, then I kind of thought, well, maybe that's actually harder than doing all the planning part. And maybe the simulation that I wrote, where I assumed that picking up a cup would be easy. If picking up a cup is really hard, then maybe my planning system wasn't really better than the other people's planning system, because they modeled the cup pick up more accurately. So then I decided that if I wanted to make sure that my research in AI is correct, is not founded on castles in the sky or great ideas about what the world should be like, it actually has to be performed in the real world. Which is why I got interested in intelligent robotics. So I decided if I wanted to prove that my system is actually able to do these things that I claim, then I have to do it in a real environment, not in the simulation. Because in the simulation, I can always cheat. So for example, if my robot doesn't work very well, if I set the noise in the vision system to 10%, then I simply tune it down to 5%. Then it works. And if that doesn't work, I can set it to 0%. So in 1997 then, we started working on our first robots together with my students. They were very simple. We had a global vision system. So there was a camera mounted on a tripod overlooking the playing field. And our robots were simple toy cars that we bought from the department store. They were remote controlled, but we replaced the remote control and connected it to a computer so that the computer could drive the car. And then this is the kind of things that we did. Going back to way back in time here. This was our first challenge. The robot is driving a letter A-shaped racetrack that you can just see with the points there. And actually it's doing quite a good job. For that time it was pretty impressive using the very simple toy car electronics and sensors, just using a vision system. And the thing that we actually used the neural network to detect the position and the direction of the robot. As you can see, at the beginning, our robots had colored markers for front and back. And then here, we just have a blue ball mounted on top of the robot. And here we did the treasure hunt. So here the robot had to drive over 5 randomly distributed points on the playing field and then sit on top of them for 5 seconds. And then drive to the next one. And then the planning problem was to find the shortest path. Now, that's a little bit more difficult if you have a car robot instead of a differential drive robot with just 2 wheels, because with the car, we cannot move sideways. We cannot turn 90 degrees. And then we got involved in different robot competitions. So one of them was playing soccer. So that year, 2004, we actually won the world championship in this particular league at the RoboCup competition. Here you can see the robots with the different colored markers. My team is the one with the yellow markers here. And then these robots were actually built out of the Lego Mindstorms kits.
Yeah, I think we stole a free kick. And, yeah, it's like a soccer match, like all throw-ins, goals, and everything.
And then one other project that I like with our global vision system setup is we build really small robots using motors developed by Citizen, the watch company, because they use those motors in their watches. So then we used the television, and we had sort of a mixed real virtual environment. So we implemented Pac-Man. Building a little robot that can pick up balls would be very difficult. So here we just simulated the ball pickup. And students implemented the sounds and everything of the original Pac-Man game. Now, one problem, of course, are the walls. We didn't really put walls on there, so the Pac-Man could go through the walls if it was programmed incorrectly. Now, one team programmed the Pac-Man, the other team programmed the Ghost, and they had to chase each other. And you can see now that the Pac-Man is working quite well. The Ghost is not working very well, right, at the beginning. But then the Ghost caught the Pac-Man, then it's game over. Now, if you were actually there at that time, then most of the teams thought that the Ghost team was doing much better than the Pac-Man team. So everybody expected the Ghost team to win. They made one change before the competition started. In training, they were basically running flawless. They made a single mistake, not a mistake, they made one change before they started, and that's why their robot turned out to be acting like this. So they had very good AI and everything, the Ghost team. But you can see it's not very effective at this in this particular match. The only change that they made was they replaced the batteries in the little toy tank that we used in order to play the game. And before, so hours and hours of testing before, these little remote control toy cars, they don't have any control that says turn 10 degrees, right? The only control you have is you can say start turning to the left, then the robot will start turning, and then eventually you have to set it a stop command. If you send the stop command at the right time, it will have turned by 10 degrees. If you send the stop command too early, it will only turn 5 degrees, right? If you send it too late, it'll turn 40 degrees. So they had tuned the robot with the old batteries. So when they designed the times and they tuned the timing command for their turns, then the batteries were weaker, so the robot would turn slower. Okay? When they changed the batteries to a new fresh pack, which usually sounds like a good idea, but often for robot competition it's not. Now they had a much stronger battery, so the robot with the same time would turn faster. So that's why when you look at its behavior, it's moving in the right direction, it's turning the right way, but it's always overshooting the direction that it turns. I mean, it always overshoots the turn. Instead of wants to go there, but it always turns like 90 degrees. This is why they lost this particular competition. And the importance is not, the reason why I bring that up is not because of batteries or this particular team not knowing what they're doing, but because I can guarantee you now, if you run various robot simulators, the latest generation, the state-of-the-art for ROS2, Gazebo, or Kokomo, none of them implement anything about battery voltage or how much charge you have in the batteries, right? So if you use a simulator to develop your system, you never come up with an idea of, oh, by the next time we have ran that same competition, all the teams learned from that experience and they had an adaptive system. They learned the control function, how good the batteries are, and the robot would adjust while it was playing to control its turns to make it act accordingly. Nobody thinks of that when they're working in simulation only, right? Because you assume you have power, you assume it comes at a constant level. But actually implementing that turned out to be very tricky because the robot is turning. You're trying to detect when the robot is going to reach your target orientation, but you have a lot of noise in the vision system. So that's very noisy. So then for short turns, small turns, you don't know if it's just the vision system that is moving the robot or if it actually is turning, but it's turning at a slow rate. So that's what makes robotics interesting. And also it is one of the challenging obstacles that we have to overcome. So that was how we started robotics. Then I moved back to Canada in 2002 to the University of Manitoba in Winnipeg, Canada. And there we started working on humanoid robots, which is what my research focus was for the last since 2002. Here's our sprint competition. We take part in the FIRA, Federation of International Robot Athletes, competition where we have about 50 teams from all over the world competing against each other in a decathlon. So a single humanoid robot has to perform 10 different events. And here's our sprint competition. I think that was Kaohsiung 2017 or so. So this is pretty interesting challenge for the robot. One good thing about using sports is that it's immediately, to the lay people, it's even clear what you're trying to do. So if I say we're having a sprint competition, then everybody knows you're trying to get the maximum speed on a short distance for your robot. So what the robot has to do here is walk forward 3 meters and then walk backwards 3 meters back to the start line, and then the fastest robot wins. So one of the other advantages of using sports is that you can actually measure the progress of the teams throughout the years. The world record in the FIRA sprint, we added the backward leg in 2012. So at that time when we ran it, the world record was 1 minute and 7 seconds or something. The current world record is 23 seconds. So you can see that there is actually quite a significant improvement in the performance of the robots. Also, adding the walking backward part is pretty interesting. From the kinematic point of view, the robots actually have no preferred, or shouldn't have any preferred movement direction. So they shouldn't be walking faster forward than walking backwards, because they're not human muscles, they're electric motors, and they're exactly identical. Like they turn right clockwise or counterclockwise at exactly the same speed. That doesn't make any difference. That's just switched in the H-bridge, where we change the direction of current flowing through the motor. So in theory, they should be able to walk the same speed, but as you can see on the backward leg, the robots are all moving slower backwards than moving, they're faster moving forward. And the reason for that is, if you look at the playing field, the robot has to stay within its two lines. If it touches a line, it has to go back to the start the whole thing from scratch, which means that then you have a huge penalty. So you have to stay within the lines. Now, if I'm walking forward and I'm starting here, and this blue bag is my target, right? Then the strategy that I can follow is very simple. I walk forward, then I detect where the bag is, then I turn my robot to face the bag and keep walking forward, right? Because I tell the robot to walk forward, it's not going to walk forward exactly. There's always some noise, so it's going to end up looking this way and being off to here, for example. Or maybe it'll end up here and facing this way. Doesn't matter, it'll turn towards the back, move forward. Then, if it does that often enough, it'll reach the goal. So we can do that very quickly. The algorithm is very easy to implement. But walking backwards, that's a lot harder, because if I'm now over here, I'm walking backwards, now I'm over here, I'm facing this way. Now I line up with the bag. I can do that. I can keep walking backwards, but then I'm going to walk more and more out of bounds. Right? So the difference, walking forward, all I need is a point reference in the world. Walking backwards, I need to have a line reference. I actually need to know where the center line is, because otherwise I'm going to drift more and more towards the edge of the playing field. Now that requires vastly different approaches, even though I have to admit, when because I was on the one designing the rules for this, when I thought about when I designed the rules, I had no idea that there was such a subtle difference. This is why you have to do it in the real world. So then teams have different approaches for that. One is to use three-dimensional markers. You can see the team here. They actually use a ball with a background behind it, and then the foreground and the background is going to shift relative to each other depending on the location of the robot. So that's what gives them a line reference, right? Now they have 2 points. Through the 2 points they can draw a line, then they know where the center line is. Other teams simply walk slower, which means that they have less error in the backward walking. The faster, the more you push your robot, the more chances are that it stubs its toes and it's going to turn one way or the other. The more error you usually have in your robot system. So here is, as I said, we're doing a decathlon, 10 events. The reason for that is that for a humanoid robot, if you focus on a single task, you never end up with a humanoid robot design. Doesn't make sense from an economic point of view. If you want to deliver mail in an office and you don't need to worry about stairs, if there's an elevator in the building, then you design something with wheels, with a little tray and a little camera and a screen, a LiDAR sensor. That will run much faster, much more robustly, much cheaper than a humanoid robot would be able to do. If you have stairs, then you can build something with tracks. It'll also be better. If you want to clean the windows, build something with suction feed and a little wiper. And if you want to wash the dishes, you build a dishwasher, right? So we already have some of those household robots. Humanoid robots only make sense if you want to have a single robot that can do all of these tasks. And that's kind of similar to humans in the animal kingdom. Humans aren't actually the best at anything. If you think about it, cheetahs can run 80 kilometers per hour. How fast can the fastest human run? Usain Bolt, world record on the 100 meter. He runs at, I think it's 48 kilometers per hour or something. It's a top speed, right? So that's extremely fast. None of us can run that. Otherwise, you'd be in the Olympics. But cheetahs can run 80 kilometers per hour and you don't even hear them. They're that smooth. Swimming, dolphins can easily outswim Mark Phelps, and climbing, no human can climb as well as the monkey. So we're not the top in any of these events. Endurance, ostriches can run a marathon in 45 minutes. But humans are special in the sense that we're in the top 5 of everything. So our swimming performance is not as good as a dolphin, but much better than a monkey, for example. Or a dolphin climbing trees is just impossible. So I think this versatility is very important in humanoid robot design, which is why for the FIRA Eurocomp competition you have to perform 10 different challenges. And so one of them is the sprint, the other one that looks kind of fun is marathon, data. Weightlifting. So for weightlifting, we didn't just want to measure the strength of your shoulder muscles or shoulder motors, not muscles, shoulder motors. So this is really a balancing vision problem. So the robot needs to walk first 50 centimeters up to the bar, align itself with the bar, and then pick up the bar. So now the center of mass changed dramatically, right? Because now it's carrying a heavy weight low. So the center of mass will have shifted downwards. Now it needs to walk and navigate 50 centimeters. With at least one foot touching the next line, he has to lift. So that's good. Now we're touching the line. Now we have to lift the bar above the head and walk another 50 centimeters. So now the center of mass is much higher, and you can see how the robot needs to adjust its walking gait to these 3 different configurations. Then we have soccer and Spartan race, extreme mobility challenge, where I was actually quite happy. Our team was the first team to be able to climb the rope. So then the robot has to climb up the rope. So here's some of the other ones, team doing archery. Basketball. Now, nobody's actually able to dribble the ball yet. That would be extremely difficult, extremely challenging. So here we just do a throw, and the different lines, you can do a 3-point throw, weightlifting again. And here's the Spartan race, one part, where the robot has to climb a ladder. The spacing of the rungs is not uniform, so the robot has to detect where the hand and the footholds are, and then climb up. And lastly, this is
innovation doesn't happen on its own. It needs leaders to drive.
Here we're working with trying to develop a rock climbing robot. This is something that we do in the motion planning course. So the interesting thing there is that it's impossible for the robot to pre-program all the motions. Like for soccer, I only need about a dozen parameterized motions: walk forward, walk backwards, shuffle to the left, shuffle to the right, turn to the left, turn to the right, kick with the right foot, kick with the left foot, and then when I fall down, I need to be able to stand up forward and stand up backwards. This one is much more challenging for the motion planner because there's basically an infinite configuration space for the motions that I need in order to be able to climb to the top. And another research project that we've been working on that I like is robot magicians. So we develop robots, humanoid robots that can play magic tricks. Do you speak Chinese? Yeah, a little bit. Okay, then maybe you can hear.
So this is all the setup for the trick, right? I talked about the research, the research goals, which in this case are actually nonsense. But it's a nail and or bag and spike trick. So there's a spike, and then obviously somebody has to have their hand smashed on top of it to make sure. And there's 1 in 3 chance that it actually happens. So the 3 bags, you need to pay attention to this bag here, the yellow McDonald bag, as opposed to the other bag, right? That's where the nail is in. So now nobody wants to step forward because they all think that they have to put their hand on top, and given how often robot demonstrations work, I can't really blame them. So now I just tell some nonsense about the vision capabilities of our robot. So now the student mixes up the bags. And what people think is that we can do a good job tracking the bag. And this is where the whole trick starts. Green, my student, she now says, oh, well, what I told her to say, actually I don't speak Chinese either, so I don't know what she says, but basically she says that, or I'll let you listen to it, maybe, see if you think it's funny or not. So she said something like, oh, my professor wanted me to use reinforcement learning, deep learning, in order to detect where the bags are, but it's really hard, it never really works so well, but I still want to graduate, so please, I always put the bag in the middle, so whatever you do, don't say the middle, right? Otherwise I cannot graduate. So this is a whole joke. And the joke, of course, is that she says that my professor doesn't speak Chinese, so I can actually tell you this right in front of the professor, right? So she just told the volunteer saying, I want to graduate, please, please, please don't take the center one. I always put it in the center. All of this other stuff never really worked well. So that's why they're all laughing. And again, pay attention, so the back with the spike is the center one, right? So now most volunteers are nice. They don't pick the back, the center one. They don't want to hurt me. So this guy said left. So this is a nice volunteer, right? He says right. So if they choose right, so now the robot crashes, right? So now the robot says, oh, this is not safe. But now nobody says anything, right? Not one person says, oh, please stop. Something went wrong, it crashed. So they all let the show go on. But then the robot magically moved the spike. The spike is actually now in this particular bag. So this is a pretty fun magic trick. It works particularly well with the Chinese audience because then they can, now they're all like, where did the spike go? Now everybody's confused. And I'll show the video of Macau. Another magic trick that we did with the computer vision class, so that was actually to give you an idea of what the assignments would be like, or if you consider those. This is, we asked the human to think about a symbol in their head, and we give, I forgot what they're called, symbols, which are a circle, a triangle, a star, and the water, the waves. So there's 4 different symbols. And then you ask people, and you give them a tiny, small notepad, and you ask them to write down one symbol. And they write it down, and then you can do whatever you want. You can do, I read your mind, or you can do any kind of reveal that you want. I read your mind, okay, you thought of this. Or you can force them, oh, they drew the triangle, so you do some other part of the magic trick where the triangle appears all of a sudden, saying, oh, see, that matches what I was guiding your actions, or something like that. So there are many different things you can do after that, if you are a skilled magician. We're not. But anyway, that whole trick worked by having them, we ran this on the internet, and that trick basically worked by just watching what they drew on the pad. So if you give them a small pad, the vision system, we basically implemented a vision system that would track, and now I know what they're actually drawing, right? Most people don't realize that though, so they're very surprised when you can tell them what they drew. Here's another vision problem that we did for the Dr. Eureka game. Dr. Eureka is a logic game where you have 3 glass tubes, and then you have these cards. We have 1. and then the robot has to pick up the balls and move them around from one to the other, so that you start with 2 red, 2 green, 2 blue balls, then you have to move them in whatever is shown on the card. So that's why we needed to look at the card first. And the challenge was to try and do that as quickly as humans. As you can see, manipulation with robots is still much slower than human manipulation. But we have the advantage that this particular search space is actually quite small. It's only, instead of 10 to the 80, it's only 1,500 different configurations for the balls, which means that we can search through that in milliseconds. And so we can find the optimal path. So we make the smallest number of moves in order to get, we always make the smallest number of moves in order to get it to the target configuration. And then the project that we're working on hardest at the moment is our Gogoro Scooter project. Where the scooter is the humanoid robot is supposed to drive the scooter autonomously by itself. And we want to be able to pass the driving test for scooters in Taiwan. This is actually takes place not on the road, but in a test environment. How many of you actually have a scooter license? You? Okay. Just one? Really? 2? Okay. Yeah. So, so here we're just testing out the steering, and you can see us outside with the scooter quite often in order to do some more tests. We actually have the balancing algorithm, but at the moment we're trying to implement some more safety measures, so things like that don't occur anymore. Like here, the scooter actually, it wasn't even a software or anything like that. We powered the robot off, so the robot was turned off, and the scooter was still turned on and not on the wheel. And then the arm, just because it was turned off, the arm just slid down and then the gas went off and it took off. So since then we added a bunch of more safety features, because this is obviously can hurt people. So we have to be more careful. Our only safety feature that we had was a student with a rope that was running beside the scooter usually, and a bungee cord on the brake handle, and then with a wedge in the brake. So when the student ran and pulled the rope, then the brake would attach and the scooter would stop. But we now added different levels of security everywhere. And we also make sure that even turned off, the scooter is always on its stand when it's turned on, and we don't want it to drive anyway. That was our mistake for this particular part there, something that we haven't considered. Now, the scooter driving project is actually kind of interesting from many perspectives. For computer vision, the fact is that you actually need, in order to balance the scooter on 2 wheels, you actually need to know the current velocity of the scooter very accurately. And so GPS is only accurate to within 10 meters, so the velocity measurement of GPS, in particular in an urban environment like here at NTNU, is not good enough. IMUs measure acceleration, not velocity, so you need to differentiate the signal in order to get the velocity, which is very noisy. And so we actually use vision optical flow in order to try and determine how fast the scooter is currently driving for the balancing controller to then select the correct steering angle. So there's lots of vision problems involved in this particular project too. Okay, good. So that's it as far as I'm concerned with my introduction. That took a little bit longer, so now I'll give each and every one of you a chance to introduce yourself to your classmates. So please say your name, your university background, your background in programming and robotics and computer vision, what kind of programming languages you know, for how long, which programming languages you like and you don't like, your hobbies, and the last book that you read. So we'll start with you then. Well, read that. Yeah. You can go first. Name, university background.
My name is Kevin, and I graduated from Antwerp University. And my major is Department of Information. And I know many programming languages such as Python, Vue, and Java XML. And
Python and what?
Vue.
That you. Okay.
And Java XML. And I have participated in many robot competitions. And my hobby is playing video games.
Okay.
And high school, high school I really want. Actually, I have read a book. I haven't read a book in a long time.
And then what do you read online?
I watch a video.
Video
YouTube.
on YouTube, okay. Okay, yeah, I guess that's a generational thing. I just hate YouTube videos for learning things. I think I could get a lot faster by just reading in text. But okay, thanks. Then next up.
Okay, my name is Max, and I'm from NTNU. And
Your master's or bachelor's?
I'm second year for master degree. Yeah. And then I learned Python and C++ before, and my hobby is play video games and anime. And the last book, I'm not sure the name of the book, but I take some books like for research or deep learning.
Yeah.
Okay. Someone for that.
Okay. Okay. Good. Yeah.
Okay, everyone. I'm Tyler, and I'm graduated from NTNU Electrical Engineering. And I'm now the second year master degree. And my main language is C# for 6 years, and Python for 4 years here. The projects I made, the biggest one is a distributed AI system that use the front end to capture images and send back to the back end and do some processing and later on display the object detection results. Yeah. And the hobbies, I like to do some powerlifting and bodybuilding. So those weightlifting things are interesting to me. Yeah. The last book I read is the Bible today.
The Bible.
Yeah.
Okay. Good. Next up.
Good morning. My name is Raffaele. I'm currently studying in NTU ST for the master's degree. So this is my first year, second semester, and I have a background in pure computer science. I graduated in bachelor's in computer science back in my country. I'm from Italy, and I have let's say a stronger background in fundamental computer science rather than robotics. But I'm taking the course because I'm working on Slalom for my thesis. So I'm really trying to, let's say, catch up as soon as possible on plenty of topics of computer vision because I have a lot of background on that. And so my main language would be Java, but I'm trying to learn Python very quickly because every application, everything is in Python these days. And yeah, and as my hobbies, I don't know if many people would consider as a hobby, but I'm trying to learn Chinese.
No, that's not a hobby. That's a full-time job. The one thing that all the foreigners, and I have lots of foreign students in my lab from France and Korea and Indonesia and Turkey and other places. And the only one that actually improved a lot in his Chinese were the ones that went to the MTC and took the course where they worked basically 3 hours per day for a long time.
Yeah.
And we had one student of mine, colleague, another professor that came to visit me for 1 year on an exchange. And he stopped doing it after 5 months, 4 months. He stopped doing it after 4 months. And the reason why he stopped is that he studied really hard, and his teacher is like, "Oh, you're really good. You're like the best in the class. You're amazing. Very good. I'm so happy with your progress in Chinese, and it's getting better and better. And maybe in 5 years, you can learn how to read the newspaper, right?" And then he's like, "Oh, that's crazy. That's like way too much commitment, 5 years of this." Because you're from Italy, I'm from Germany. I can learn Italian very quickly, and you can read the newspaper in Italian in about 6 months, easily enough. And if you want to learn German, it will be the same. Or I can learn Dutch. Actually, I learned Latin, so then I can probably understand quite a bit of Italian already, or Spanish, or Portuguese. So that's a kind of level of commitment that in Europe we're used to in order to be able to learn a second language is sort of, you can get to a level where you can learn yourself, because once you can read the newspaper, then of course it's easy to pick up new words and everything, right? Because if you don't need to know a word, you can just look it up in the dictionary. If you try to learn to read the Chinese newspaper, then I have no clue where to find that in the dictionary, because I need to know what the root is and how many strokes. And I'm like, if I know all of this, I already know what the character is, right? It won't be an unknown character at that point. So yeah, a lot of the foreigners, but I wish you luck, and you should try.
The issue is that at the beginning you have plenty of motivation because it's easy. At the beginning you make a lot of
progress. You make a lot of progress very quickly.
1 year it becomes slower and slower and slower.
Yeah. And the problem is you really need to take a course, because I never took a course. My wife is Taiwanese, so I basically only learn from talking with her, but then the problem is you talk the same things all the time, right? Or I can deal with the office, like, 我上课我需要钥匙 they give me the key, then it's okay. But I don't learn any new vocabulary, right? Unless you're forced to in a class. So yeah, good. I wish you all the best of luck. So I think that counts as a hobby / part-time job.
Yeah, definitely. And yeah, last book I read, I read a bit of philosophy with a bit of a passion. I try to balance the computer science and the human part. So I try to read a bunch of about ideas and stuff, and also to understand more about Chinese culture, which is huge. Guys, your culture is concert and Lao Tzu, it's incredible. Tao Te Ching. So I try to catch up on all the stuff I miss. Because in Europe, we're very Eurocentric, maybe when we study.
Well, I mean, Italian culture, the Romans were kind of influential too.
That's one.
Okay, thanks. Next up.
Hello everyone, my name is Fan Jinqi, or just real in English, and I'm from NTUSC, majoring in computer science, and this is my fourth year. And I've done some projects such as some computer graphics in C++, doing something like just transformation matrix computation or simple computer science in Python. And my hobbies is watch movies online and about the last part. In fact, I haven't read for a long time.
So, what's the last movie you watched that you liked?
One of my favorites is Inception.
Inception. Okay, that's the one with the dreams, right? Going in the dreams. Okay, yeah. Right, thank you. And actually, yes, we in our course we're dealing with computer vision, but computer graphics is kind of the exact inverse problem. That's why quite a few of my students actually ended up working in Hollywood for the movie studios, even though they did their research all in robotics and computer vision. Basically, the fields are very related because for computer vision, our problem is that we have a picture and we need to figure out what the model of the world is, right? There's a chair at this location, there's a table, there's a human male sitting there in a blue sweater, there's a human male sitting there in a brown jacket, so on and so forth. So we have the picture, we need to know what the model is. But in Hollywood, in computer graphics, it's exactly the opposite. They know what the model is. Wonder Woman flies from here to there, and they need to know what the picture looks like. One of my students was the director for motion capture, the second person for the motion capture for Avatar, for example. So she did Avatar, and another student of mine did Journey to the Center of the Earth 3D, which was quite a popular movie. And Lord of the Rings, we also did with Vika. Okay, last but not least.
My name is Amy, and I'm now a university student studying in NUSD and fourth grade. And I have no rapid background. And I major in computer science. And the project I have made recently year is last year the course of compiler and we made a simply compare, and it's a little bit hard, but it's um, great.
Yeah.
And I usually write C++ and Python and a little bit HTML and backend language. And my hobbies in my free time is baking and cooking. But
Oh, no food, no proof.
Yes, and so the next book I recently read is recent about tart, like lemon tart and chocolate tart.
Okay. Yeah, that makes sense. Yeah. Okay, thank you. I think I skipped you, right? You haven't introduced yourself yet? Yeah, you.
My name is Boy, and I present work at YDU Yuanzhi University at Taoyuan, and I major analog IC in my university.
Analog IC.
Yeah.
Okay.
And when university freshman year, I learned C++, and now last semester I learned Slang, and my project is program builder combined occupancy agreement, and then my head is
And that's here at NTNU?
yeah. And my head is sport play basketball.
Basketball.
Yeah.
And the last book you read? The last book that you read?
I forget.
You forgot. Must have been a pretty boring book. I guess I didn't tell you what my last book was, but it's I think it was Glenn Cooper, which is, it's a fantasy novel, but it's like a detective story. It's like there's wizards and elves and magic, but the main character has to solve a murder case in the elf kingdom. So that was fun, interesting. Okay, good. Then today I want to start with a simple, I assume that most of you are aware of how we represent images in a computer. So if you use Python and you do computer vision, then most people use a library called OpenCV. How many of you have heard of OpenCV before? 1, 2, 3. Yeah. Okay. So that's a library that deals with a lot of the technicalities of reading in an image and putting it into the memory of your computer for further processing. And it also has a lot of powerful, interesting algorithms for computer vision processing. So you don't have to implement them on your own, and you don't have to implement them in Python or as a C++ wrapper. Now, when you get an image from OpenCV, then what format is it actually in? It's a matrix, yeah? So for an image, we have a 2D array or a matrix. And that makes sense, right? Because if we have an image, there's sort of an x and a y coordinate. Now, usually the x and y coordinates are different from the way that they are assigned in mathematics. So usually y goes upwards in a mathematical graph, but in an image, 0 is at the top, and then we grow downwards. And how about the information? Now, this matrix consists of picture elements, or short pixels, right? And what's the format of the pixels? The most common one you're dealing with? 24 bits, yeah. In, it's called RGB format. So that means we have 8-bit of red information, 8-bit of green information, and 8-bit of blue information. And that then is also the way that it's composed on the monitor. So if we send that to a monitor, then that's going to look correct. More or less, if you are a digital artist, if you create artwork, then this mapping has to be much more accurate. If you're trying to get it done on print, for example, you want to print it out and show it in a gallery or something like that, then the colors need to be exact, and there's a whole bunch of additional complexity in order to match the colors accurately. You may have heard of the Adobe or the sRGB standards and things like that. For our purposes, this is what we usually get, and let's see how that works with a little example. So let me start. Now, for the teaching, most of the lecture slides are actually Jupyter notebooks, so you can download them and run them yourself, and you can modify them and try out different things with them. Now, I actually want to try something new today. So we're going to start. What's that? So here I just need to set up a bunch of stuff for my teaching. And we incorporate some often used libraries, in particular the Matplotlib library, the NumPy library, math and random functions, as well as OpenCV, the second version, imported as CV2. So we need to have an image, so let's pick the Doesn't Google now have the image generator built in, or is it only Bing? Valley, you need to have a token. I don't have any stable diffusion built in. Okay. Let's see how that works. What is this asking me now? No. Keep signed in, no. Okay, so there's the picture. Foreground. This takes too long, or what does it say? Okay. Yeah, I can try that.
If you like this, I can send this to you.
Okay, yeah.
I'm gonna try it.
So just post it to the Robot Vision channel.
All right.
You should have the. Are you uploading it?
Yeah, it's in the Robot Vision something.
No, you posted it to. Okay, but that's okay. Save the image. Repeat. So now what happened? Because that image is not the same, right? Something is wrong between the original image and what we display. And what is the problem? If you look at the code is actually not doing much. It's just calling read the image. And my function here simply takes a URL and downloads the image and puts it in a database so I can use it later on. So I'm not doing any magic manipulation there. So the problem is that the OpenCV library is expecting the image to be in, instead of RGB, OpenCV usually works with BGR images. Okay, they're all 24 pixels, 24 bits, 24 bits. Here we have 24 bits. But the RNB components, so the red and the blue components, are swapped. And that's then, if you get this wrong, then instead of having orange face here, you end up with the blue face. So this happens quite often in first implementations. Here the red and the blue channel are simply swapped. You can also see this red book here is a blue book over there. And what we actually display. And why does that happen? That happens because when the computer actually processes the pixels, the 24 bits, those are extracted, and these 24 bits are represented as an integer then, actually a 32-bit integer. And now, if you have a bit pattern, there's two possible ways in which you can interpret it, either as little endian or as big endian. This is actually taken from a book, Gulliver's Travel, which is the first science fiction novel ever written by Swift. And in there he comes to a planet, and there's a big civil war going on between the two groups of people. One of them, they eat the egg, a hard-boiled egg. If they tap it, they tap the smaller part. And the other one tapped the bottom part. And they've been fighting a war for 100 years about which one is the correct way to peel the egg. And the whole thing is a satire about the stupid things that humans fight over on Earth. But anyway, this is where this is taken from. Intel is a little endian architecture. Okay. ARM is also a little endian, so that the major processor families nowadays are both little endian. There's really no right answer. There's a small argument to say that little endian is slightly more efficient as far as the transistor count is concerned when you implement the logic. But nowadays, when we can build CPUs with billions of transistors, saving 100 transistors really isn't really that much of an advantage. OpenCV expects it in the BGR format, I think. So our image library converts it into stores it as RGB when we read it out as a 24-bit value. If the little endian, big endian mapping is incorrect, then you end up with the completely wrong color information. Now, what we have to do is we need to swap the red and the blue channel. So how can we do that in Python? So now the problem is we have a 24-bit array, and I want to swap the red and blue channel. Then what kind of Python code can I write in order to swap that? So you can write something like this, swap red and blue for the image and then return it. So you can now define a function. And then try and implement that yourself so that you can run this code and the image here looks correct. So I'll give you 5 minutes to do that. Now for the course, make sure it's easier if you bring your own laptop, have your own Python environment set up. You can also use Google Colab like I do if you want to, but that requires quite a bit more work to get certain things going. So it's depending on how experienced you are in Python and programming in general. I think it's easier to just run your own local Anaconda or Conda environment. So now implement this function here, swap red and blue. I want to pass in an image, I want to get out an image. You can do it destructively. So just return a pointer to the image with the red and the blue channels swapped. Just continue with it, just swap the red and blue channels. And the rest of the code you can just copy from. There's actually a bunch of different ways you can load an image. If you don't like the way I'm doing it, you can also use your own method to load an image into memory, but then implement your own function to swap the red and blue channels. And if you haven't done any Python before, then make sure that you install it and run print hello world in order to make sure that you can run Python code. You have to make sure you plug it back in whatever you do afterwards. Right? When you plug it out, you have to plug it back in, otherwise you will get any errors. And once you're finished with your swap operation and it works, then you can raise your hand and I'll have a look at it. That I've never heard of. Maybe. But it doesn't matter. I still want you to write that function. You want to cut all of those. These are only needed for my teaching. No, you don't need that. You just need to copy just delete those from the notebook. Yes, you just delete them. You don't actually need that, and you also don't need. This is only to make the PowerPoint start presentation. If you want to, it'll run. You can execute it, and it will run. You can just execute this cell on your own notebook, not on mine. You'd have to download it or copy it yourself, or just start copying from the next code cell. Okay, now when you're running it, you can just run it and just wait until you finish. But that's just to make the lecture slides this format here in the Jupyter Notebook.
Yeah, because basically also our code OpenCV C++, so kind of mentioning OpenCV as well.
Yeah. Of course, we could do all of this in C++ as well. Python is, however, the lingua franca at the moment for deep learning, machine learning, AI, and also computer vision. Yeah, that's actually correct. Okay, so that will be the first. Let me have a look at the So, since we're dealing with a two-dimensional array, we may just implement this as processing on the array. Now, it's important to realize that when we're processing an image, the image is stored in row major order. So the first thing that we iterate would be the y-coordinate, not the x-coordinate. That's something that people usually are confused with, or that when they mess things up. So I can generate a y-coordinate as over the length of the image, and that will be the number of rows that I have in my image. Then I can generate the x-coordinate. Now, in theory, we know it's an image, but it doesn't necessarily have to be one. It could be a triangular image or something like that. So I can take the length of the array y, image y, and then I can swap them. So red is image 0, temp is image 1, red is image 0, temp is image 1, then image image 2. Image 2 is equal to red, and image 0 is equal to 10. And then I want to return the image, which is not a copy, it's now destroyed, right? But it will have swapped colors, so it should have swapped colors. So then let's try that. It's not out. Image y, x, of course. And then now my colors are correct. So that would be the simplest way to implement that. It's not an efficient way. Often you don't need to remap the image. For example, if you convert it to grayscale afterwards, for example, there's no point to do any color corrections. And also, since image read actually doesn't generate an arbitrary two-dimensional array, but it actually generates a NumPy array, there's faster, better ways of doing that. And that is just to show you the power of the NumPy arrays. I can actually do that in a single line by saying that the image is the image for all colors, for all columns, for all rows, for all columns. I want to start at the first index and go to the last one, and I want to increment by -1. And that will actually take an RGB, a three-dimensional array that is in the form RGB, and convert it into BGR. So we can actually do that in a single line if we have to do it for display purposes. And then you can say, see, this is also correct. is correct here. I have to scale down my images because Google Colaboratory only gives me a limited amount of RAM. Otherwise, the rendering will take too long. So, but you don't need to do any scaling of the input image if you run it on your own local workstation. It'll be easily fast enough. Now, let's do another thing. Let's create a new image from scratch. So images are always 2D matrices of pixels, but the pixels are 1D arrays encoding the color in some format. So RGB how did I get this? RGB, BGR. Then sometimes you also may have heard of ARGB, or yeah, ARGB is the more common one, or BGRA. Those are 32-bit formats where your pixel information is stored as red, green, blue, plus an opacity value, like the transparency, how much you can look through the image, or other kind of image format. So I can do that. And let's generate an image. Not quite so big, maybe 400 by 300. And we would use the NumPy array functionality. So we would generate an array of zeros, for example, of the format height, width, and 3 channels. And okay, if you want to, you can define a data type here. For example, uint8, which would make it 1 byte per color channel. So that's usually what we have with our images. Then I can set every row columns from 0 to 200 and from 0 to width divided by 3. And channel 0. And I set that to 128. Then I can show the image. Now we should have the left third columns. There should be a bar that is half the brightness for that channel, and then we know what channel, what value the OpenCV library actually expects. So in OpenCV, it's RGB because I'm painting 0 here, right? And if I set that to 120, if it's all zeros, it's black. If I set this to 128 or 200, then it'll be a big array. So now I want to try that. See how that looks like. Okay. So from width divided by 3 to 2 times width divided by 3. Channel 1 I set to 200, and here I wanted to do the multiplication first to avoid rounding, to minimize rounding errors. To 3 times to width. Two is 200. So then we get this image here. And what's interesting about that image? So now the pixels on the left-hand side are simply the red value 200, and the other channels are 0, 0. Right? And in the green channel, here it's 0 for red, 0 for blue, and the green is 200. And here the blue channel, it's 0, 0, 200. Right? So every pixel is has a value of exactly 200. So when you look at it, you would expect that the brightness of each of these 3 bands, the red, the green, and the blue band, should be the same. Right? Because I set it to 200, the same value over all 3 of them. But when you look at it, then what do you see? the green seems to be much brighter, right? And the blue is quite a bit darker than the green. So maybe that's just something to do with our value. Let's try some other values. Maybe if I don't set it to 200, let's set it to 128. Improvement over here. So here I think green still looks brighter. The difference between red and blue is not quite so big anymore, I think. That would be my view. Now, so what I'm trying to get at by doing this is that apart from teaching you how to use NumPy arrays, powerful functions, is that actually color perception is not as clear cut as you think it is. We can also try and set it to a maximum value, 255. And now it's pretty clear that green it seems a lot stronger than the blue one and the red one. Because when you start doing computer vision, then and robotics, you want to kick a ball, for example, with your soccer playing robot. Then we started out with an orange golf ball or a tennis ball. And you would think that, or you take some task and you want to have a smart watchboard, and all you have to do is track the blue marker about what the teacher writes. And you think tracking this marker should be pretty easy, right? Because it's a blue marker. If you ask your 3-year-old nephew where the marker is, where's the marker, he will get this right 100% of the time. No sweat. Very easy for, you wouldn't say, oh, you're a genius. You're so far outperform every computer vision program we have written by the smartest people. MIT, Stanford, Carnegie Mellon University don't have the professors that are able to write a computer program that can track a blue marker through an environment without making errors. And that has to do with color perception, because actually your human brain does a lot of processing, and it's the way that we perceive color is only after the brain interprets it. And you may remember this one. This one broke the internet at some point. Yeah. Right? So we had the picture, the original question, if you haven't seen it, I guess. Whether you see this as an orange or a white dress, people could not agree on that. Where's the original image? So this was the original photograph of the dress, and then what color do you see this is the dress? What color is this?
I see it as blue and black, black and blue.
Black and blue, yeah, me too. Anybody sees it differently? Some people, a lot of people, sort of 50% of the people see it as orange. And the fact is, people were starting to think this was some kind of hoax, where 3 billion people were just convinced to play a joke on the other 3 billion, right?
It's white and gold. Many people see it as white and gold.
Correct. It could be white and gold, or orange, or black and blue. And whichever one it is, it's what your brain focuses on first. Now, the original color is actually white and gold lace. So this was hugely popular. People had huge discussions about that. The dress is actually black and blue, but there was no white and gold version available. So some people saw it as this, some people see it as this. This is the actual photograph that was taken, and it just happened to be sort of at the 50% level of brain decisions that people were making. If you see it as one color, it's impossible to see it as anything else, and you would never think that you would need to argue about what color it is. But what happens is that it depends on how your brain interprets the shadows and the lighting conditions. If it thinks that there's a very bright light, then this translates to a brighter image for the dress. If you consider this to be in the shadow, then your brain will swap the colors around very dramatically. So the color perception is not as easy as you may think, and even things like this here, you can track the brightness response that people see for different colors, and instead of being a cube with RGB values ranging from 0 to 255, it is actually quite a much more complicated shape. I can So this is related to the physiology of color perception. Where are the charts? It looks much more like this. It's this kind of shape, how your brain responds to changes in color. So it's not a cube or any other kind of simple geometrical shape. So one interesting result of this is having a look at the following lecture slides. So here I load in an image. From our lab that was taken last year. Then we deal with the endianness. That gives us the image. And now I can take the image and I can generate it into individual channels. So I can take the red color channel and convert it into a black and white image, and the green color channel, convert it into a black and white image, and the blue color channel. So this is what we did here. And here's the red channel on the left, the green channel in the middle, the blue channel on the right-hand side. And now we can do some fun things with it. I implemented a function compressing the plane, which takes the image, calculates the average of a particular plane, and then scales the image with the max and the min value. So the average of the brightness is not going to change. It's only the ups and downs of that average. So the variance, we reduce the variance in that particular plane. So we take the red image, and if I plot the value along a row, for example, for the red channel, I may get something like this. And the average would be here. And then by compressing it, I generate this kind of value. So it just goes a little bit above, a little bit below. Right? So that's what the compress function does. If I compress that a lot, then basically what I do is I take the entire image and just replace it with the average color. Which means that I basically throw away 1/3 of the information in the image if I compress it a lot. So for an image, we can run it and we can compress the individual colors and then generate it back as the original image. So for that particular test image, but you can use your own, the minimum was 0, the maximum was 255, and the average was 129. And after compression, it moved from 129, the average is not changed, but now it ranges only from 192 to 64 to 192. And green was from 0 to 255, and now it's changed from 64 to 191. And blue was also from 0 to 255, now 62 to 189. So here are the individual channels, red, green, and blue. And the compression factor that I used was 2 in this case. Here I compress it by half. So then I can show the image. And you can see that compression, if I compress the red channel, here the red channel is compressed, the green and the blue is unchanged. Here, red and blue are unchanged, green is compressed, and here, blue is compressed, and red and green is unchanged. So only one channel is, I make some modification to it. And what do we see in this particular channel, in this particular image, is that if I compress green, then it totally changes the image. Right? This is quite a strong distortion in the green channel. And also the red one, but not nearly as big as the green one. The green one, here the image is weird, right? And the blue one actually looks pretty good. There's not much change here in the color information. So I can do that more extreme and I can have different levels of compression. So here I now take the same image which spanned from before. It spanned from 0 to 254.5, right, with an average of 124. And now I compress it by a factor of by a factor of 400. So instead of 2, I divide it by 400, which means that basically that entire channel is simply replaced by the average color. Because the range after compression, before it's from 0 to 255, afterwards is from 123.9 to 124.5. Which if I convert, then I cast it to an integer, is all 124, which is the average of the image. And similarly for the green and the blue. And then you can see the green is completely off, right? Because now there's no green information at all anymore, just one average value. And the red is off. But the blue is actually still reasonably okay. So what does that mean as far as the human vision system is concerned? That's why the lecture slide is called blue blindness. Humans are actually almost blind to the blue channel. We're not, you think you see a lot of blue, but unless it's an artificial image, like something generated on the computer, you never notice it in reality. And they've done studies, and this is why the shape of the human color perception is so non-uniform. This is also used in compression. The JPEG standard compresses images in a lossy way, right? So it throws away information. And in particular, what they throw away is half of the blue pixels. They subsample by 4, so they throw away 3/4 of the blue pixels. So instead of every 4x4 square, they only use one blue channel. So that greatly reduces the amount of data you need to store for the image, and nobody notices the difference simply because your eyes are very poor at detecting blue. We can also talk about optical illusions. Vision system is very good at extracting models from the world, right? Constructing reasonable world models. Computers are not nearly as good. Things like face recognition of their parents, little babies can do it much better than any AI system. YOLO won't be able to do it nearly as well. But that's why it's easy to fool the human brain if some of the assumptions from the natural world are not met. And the reason for that is in order to construct a model, there's like an infinite possibility of models that your brain could construct. It has to take some shortcuts and make some decisions about what's likely. It has to decide whether this dress sits in the shadow or in the bright light. And if it's in the shadow, then it will be one color originally. And if it's in the bright light, it'll be in a different color. The bright orange light, it will be in a different color. And your brain just picks one and then just goes with it. That's why you cannot possibly see it as any other color. And anybody that tells you that this dress is white and gold, you think they're crazy, they're trying to trick you or fool you or something. One of my favorite optical illusions is this one. Doesn't even need to go all the way to color. Copy image? No. Open in another tab. So of course, now what do you see here in this image? What's in there?
Top square is darker.
Top square is darker, right? So it's kind of like a pillbox or something, jewel box that is open with the bottom being white and a black part on top, right? Now, I have shown you already that I can do magic, so it wouldn't be fair if I do it, so I'll have to ask one of you guys, if you come up here, we'll let you do some magic. Because you have to believe that you can make this the same colors up and down. Do you think you can do that?
Maybe.
Okay, how?
Block those colors.
No, no need to block. No, you need to come here. You just need to really believe that you can do that, and then you can use your arm. No. Stay here. And move your arm here, like this, between there. Okay? And now what happens? I'll do the trick for you. Now it's the same color. If I put it there, then what?
Oh,
These two are exactly the same pixels. These two are exactly the same color.
so
right?
the edge.
So the edge and the shadows. So in a real world, this image would not occur like that. The edge and the shadows. So this is a synthetic image, right? Generated on the computer, which is why we can make those two. We can also introduce the shadows and the edges in order to fool your brain into seeing a three-dimensional scene, which it doesn't actually see, right? This is a 2D. There's no 3D behind it. And, but your brain looks at this and says, oh, I know what this is, right? This is a pillbox. Bottom is white, top is black. No question about it. But if I take these away, then your brain says, oh no, wait a minute, they're exactly the same color. Right? So the way that you perceive, that's what makes computer vision hard. If it were otherwise, then of course, if the blue pixel would always be 12, 92, 57, I could find that in microseconds through any image you want, right? But the problem is, even for things that you think are the same color, right? Where your brain tells you that this is the same color, the values that you actually get to your eyes, and they've done neurological studies with this, the brain actually tells you, oh, this is the same brightness level as this one. Right? Now our eyes, as chemical electrical processes, don't work with 0 to 255. They don't use unsigned bytes, but the signals coming from your eyes tell you that these two are the same, right? And then your brain goes, oh no, you guys have been lying to me all my life. I cannot trust you. I know what this is. There is a shadow, there is a box, this is leaning out, so definitely the bottom part must be a lot brighter in order to generate the same brightness level. And the top part must be a lot darker in order to generate that gray level. So I know what this is. Just shut up, eyes. And then this is what your brain sees. And then there's no way to see anything else. Unless you can fool the brain. So if I take away the three-dimensional information, then boom. So this is my favorite trick to do.
So brain considers average black and average white.
No, not average. It considers this as a geometrical shape that looks like that,
okay.
right? And if there's a light source,
okay, if there's a light source, so it consumes.
Yeah, that's why it considers the shadows here. It takes a light source, and if there's a light, and the light usually for your brain, it's the sun, right? That's the light that we're most familiar with, so it's up on top. If the light is on top, and this has a particular brightness value, that is the same as this one. But the brain knows this one is in bright sunlight, so the brightness of this patch is going to be much higher. So the original brightness of this shape has to be much lower. So your brain thinks, oh, this must be quite dark in order to generate this brightness level under the light. Whereas this part, it sees as being slanted away in the shadow. It says, oh, if this part has this brightness level, then that must mean it must be a lot brighter than what I actually read. So that's why it makes this one white and the one on top black. And in the vast majority of images that you get to see as a human during your life, this is exactly the correct interpretation. That's why you can avoid trees hitting you, branches hitting you, right? Or walking. That's why you can avoid walking into trees or off cliffs, which is evolutionary a pretty big deal, right? A pretty important skill to have. And it only fails if under certain conditions that just where the shortcut that the brain takes is just happens to be the wrong one. Or if you deliberately try and fool the brain. Okay, good. So that's it for today. One thing that I forgot to mention, I mentioned it last class, but if you weren't there last class, this class will be taught using the global virtual classroom idea from NTNU, which means that starting on March 11th, we will actually have joint classes with the students from Ostfalia University in Germany. So that means that the classes will have to be moved to the afternoon because 9 a.m. is too early for Germany. They are 7 hours, so it'd be 2 a.m. for them. So we will move the classes into the afternoon or evening, and then you will do a project together with the students from Germany, probably either a magic trick or a soccer playing robot. They have the Turtlebot robot platform, and then you would be responsible for the vision processing. So we take some vision processing, detecting the ball, detecting the field lines, or maybe the vision processing that you have to do for driving the robot outdoors, following a line or something like that, like the marathon in Europe. And then the German students will be responsible for the motion of the robot, and you'll be responsible for the vision of the robot. That will be implemented in OpenCV as well. So starting March 11th, there will be collaboration with the German students. And I also, to give you an idea, I came up with the idea for the first assignment. I haven't written it up yet, but what I'm thinking is to have because my nephews, they like to play this connect the dots puzzle. So you may have seen those. So they're kind of like this. So you have a sheet of paper, and then you have to start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And when you connect all the dots, you get the picture of a dinosaur that you can paint in. So now what we want to do is, I want to be able to take an arbitrary picture and convert it into this format. So that means a couple of things. You need to first extract the foreground from the background using Midas or some kind of latency system. And then you need to extract the contour of the object. But once you have the contour extraction is not that hard. You can do that. But once you have the contour, then there's OpenCV library calls that you can use for that. Once you have the contour, then the idea is to convert it into, then you have this already, except instead of 5 points, instead of 45 points, you have 4,000 points. So nobody's going to sit there with 4,000 points. So you need to then simplify the contour of that shape, and then you need to think about ways which you can decide which points to throw out of the contour and which points should remain inside. So I think that's currently my plan for the first assignment. But I will post it and announce it later. You still have quite a bit of time before this first assignment is due. Okay, good. Then that's it for today. And I'll see you all next week.